Hi everyone. In this video, we're going to go through section 14.3, measures of dispersion. In this section, we will look at three different terms. The first is the range of a data set, and then the standard deviation, and then the coefficient of variation. So three different topics that all deal with the dispersion of a data set, and that just means how spread out it is. Our first definition is that of range. The range of a data set is the difference. Difference tells me to subtract between the largest and the smallest data values. So if I give a test, I subtract the highest test grade minus the lowest test grade. That just gives me a glimpse into how spread out my class is in terms of their understanding of the content. So here we have our first example involving range. We have four different people, and I want to know the range of their heights, and we're given feet and inches, and then we're also just given inches over here. So we're going to identify the tallest person in the set is that Robert Wadlow, who is 107 inches tall. Shortest person in our set of four people is Madge Bester, who was 26 inches tall. We're finding the range. That tells me to subtract them. 107 minus 26 is 81. So 81 inches is the difference between the tallest and shortest person ever to live. And what you kind of notice is that difference is LeBron James is taller than LeBron James, who is a really tall individual. His height, you could stack him on top of Madge Best, or maybe you should put her on top of him, and that wouldn't be as tall as the world's tallest person to have ever lived. All right, but there we have the range, 81. Oh, I didn't label 81 inches. There we go. Next, we'll introduce the topic of standard deviation. First, to deviate means to stray from. So when we talk about the standard deviation, right, we can look at a data point, like this data point 16 right there, and how far away is that from the mean? So if I compute the mean of the values in that table, you get 17. 16 is one below 17, right? It deviates from the mean by 1 unit below, whereas 14 is 3 units below the mean, so its deviation is -3. And 21 over here, that is his deviation is 4 units above the mean. Okay, so standard deviation deals with the deviation, how far away each data point is from the mean. But if you look at the table, when we compute the deviation for each data point and then add them up, you get 0. So that doesn't really tell me any information. And the reason you get 0 is because there's some positives and some negatives. So the way that we account for that is by adding on a column to this table where we square each of those entries, and that will allow us to add them and not get 0. So let's take a look at the next slide. So the top of the slide gives us the formula for standard deviation. S equals the square root of the sum of the squared deviations divided by n minus 1. That's our sample standard deviation. All right, it's a big ugly formula, but I like to think of it more as the process of creating this table. So you take your data value, you subtract that data value minus the mean. Okay, I'll even sometimes have a column 2 there where I write down the mean. And then you square each of those data values, noting that whenever you square a negative number, the answer is positive. So -1 squared is 1, -3 squared is 9, -5 squared is 25, etc. Then what we do, the next step, is we take and sum each of those squared deviations. So I'm going to take this last column here and add 25 and 25, 16, 9, and 1, and I think you get 76 when you add those up. All right, that's the sum part here. The next step is to divide by n minus 1. So let me move this up a little bit. We're going to take 76 divided by n is the number of data points, 1, 2, 3, 4, 5. So 76 divided by 5 minus 1, which is usually 4. 76 divided by 4 is 19. And then the last step, the standard deviation, is the square root of 19, which is, let me do, approximately equal to, check that in your calculator, 4.36. So the standard deviation of this set is 4.36, and that's a measure of how spread out the data points are. This slide, I'm not going to hang on here too long, but this point really details out the steps that we follow in computing the standard deviation. All right, so let's find the standard deviation here for these flight prices. And the first step is to find our mean, x bar. And let's see, x bar is equal to, we're going to add up all the data points, 195, 213, 208, forgot my plus sign, 219, 210, 215, 215, and we're going to divide that all by 6 because there are 6 numbers there. The sum is 1,260, which divides nicely by 6 to get $210. So the average average cost of those 6 flights, $210. Now we're going to go and find the standard deviation, and I'm going to set up a table and label each column of my table. First, the prices, my x's, are just listing out the 6 flights: 195, 213, 208, 219, 210, and 215. And I like to put a column where I just write down the mean as column 2. All right, and I could write that just 6 times over and over. 210. There we go. And the reason for that is now when in my third column, I'm going to have the deviation, x minus x bar. Right, and I write that out because just to make sure that I subtract in the right order. 195 minus 210 is negative 15. 213 minus 210 is a positive 3. This one's a negative 2. This one's a positive 9. That one's a 0. That there is no deviation from the mean there. 210 is the mean. And then 215 minus 210 is 5. There's column 3. My fourth column, I'm going to square each of those x values, and then that's the last entry in this little table here. Okay, so let's see. When you square those negative numbers, the answers are positive. 225, 94, 81, 0, and 25. And now I'm going to pull my result out of the table. First, I'm going to sum all of those squared deviations. You get 344. 344 when you add them up. And then that 344 gets divided by n minus 1. 6 minus 1 is 5. 344 divided by 5 is 68.8. So our standard deviation is the square root of 68.8, which is approximately 8.29. And if you compare that 8.29 to the other standard deviation that we got for the previous set of numbers, 4.36, right? This data set is more spread out than that data set with a standard deviation of 8. The other one was about 4. All right, so that's how we compute standard deviation of just a single set of numbers. In this next example, it gets a little bit more complicated when we have our data organized with a frequency table. So you can pause and read through the setup for this example, but we're given 20 trading sessions for this software company. All right, and how their stock price is fluctuating and whatnot. And the goal ultimately is to find the standard deviation. But when we take this data and write it down, we're going to organize it in a table, in a frequency table. Before we get to the table, though, let's just real quick compute the mean, x bar. If you add up all 20 of those numbers in your calculator, you will get 800. And when you divide that by 20, the average for this data set is 40. X bar is 40. All right, so I'm going to show you what our frequency table looks like for this problem. We have our stocks closing prices listed out here in the first column. And if you go back to the previous, a few seconds ago in the video, you can look at each of those frequencies. And, or you can look at all the raw data and find the frequency for each price. So 37 appears once, 38 appears twice, 39 appears 5 times. If you add up all those frequencies, you get a sum of 20. Okay, so to continue filling in the table, and this is all stuff that we're going to need to ultimately answer the to find the standard deviation, I should say. The next column it has us fill in is the product x times f. So the data point times the frequency. 37 times 1 is 37, 38 times 2 is 76, 39 times 5, 195, etc., 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 as you go down. And if you add up all of that, you get the 800 that I previously got when I was computing the mean. So these first two columns of our table here, 800 divided by 20 is the mean, 40. So these first two columns help me to find out what the mean is. All right, next we are going to move this box over and find the deviation. So now I'm not looking at the previous column. Let me point at it here. To get this column, I go back and subtract the closing price minus the mean. 37 minus 40, negative 3. 38 minus 40, negative 2. 39 minus 40, negative 1. 41 minus 40, positive 1. Okay, you get the idea, hopefully. All right, so make sure you pay attention to what you're subtracting in there. All right, now we're going to go back, we're going to square that column. So take each of those. Negative 3 squared is 9, negative 2 squared is 4, 0 squared is 0, etc., etc., etc. All right, and then the product, all right, the last column of the big giant table is the product. There we go. The product, the deviation squared, so the previous column, times the frequency. So I'm looking, let me use my highlighter. I'm looking at this column and this column, right? The deviation squared times the frequency. 9 times 1 is 9, 4 times 2 is 8, 1 times 5 is 5, etc., 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 as you go down. And then just like the earlier problem, we sum those deviations, the squared deviations times the frequency, add them up. Okay, this looks like a fairly complicated process, but when you get to the homework, it will give you the table to fill in, but it only has you fill in one row at a time. So I highly suggest to follow the formatting of the table. Okay, follow the formatting of the table, but on your paper, write down and go down each column, because that's the order you fill it in. In my math lab, it has you fill in across one row at a time. My suggestion would be to go down one column at a time and write down all of that work, okay? And then you can just punch it all into my math lab and churn it all out one after another after another. All right. Now, to get to finish this process, we're going to take our answer out of the table and get our standard deviation S is the square root of those squared deviations times the frequency divided by n minus 1. 50 divided by 19, because n minus 1 is 19, is equal to, the square root of that is equal to 1.62 approximately. So our standard deviation for this set of data is 1.62, and that's a measure of how spread out the data set is. The formula for what we just did on that last example is right here. All right. Again, I would suggest making that table in my math lab. They'll force you to make that table. It's helpful. Okay. It's just a way to organize all of your work. Just be careful as you go through it. Here's a visual example of standard deviation. We have 3 different distributions, and the mean of each of them and the median of each of them, of both distribution, of all 3 distributions, is 5. But the first one has a standard deviation of 0.82. You can see how packed together it is. The second one has a standard deviation of 1.29, a little bit spread out. The third one has a standard deviation of 2.38, a little bit more spread out. This data is more spread out than that data, but their mean, median, and mode all are 5 for all of them. The last topic of the section is the coefficient of variation. And the coefficient of variation, denote it with a CV, is the standard deviation divided by the mean times 100%. This percentage is another measure of how we tell of how spread out a data set is. So it's similar to range and standard deviation. Okay, it's just another measure of how spread out a data set is. We're going to look at this example in dealing with Facebook and Twitter and their closing stock prices during the first 6 months of 2016. I'm going to have a video that I'm going to post after this one where I show you how to find mean and standard deviation using some fancy buttons on your calculator. And you can do that as you go through the homework. There will be some where it wants you to show some work and other ones where you can use your calculator for sure. All right. But what I'm going to do for this one is I'm going to say for Facebook, and that is this middle column here, Facebook. Again, the labeling sometimes is just missing. It's a little strange. This one is Twitter. Okay, but Facebook's mean and standard deviation are given as, let's see, Facebook is $114.73. That's the average stock price for Facebook in these 6 months, and the standard deviation is $4.67. And then for Twitter, the X bar is $16.06, and their standard deviation for this stock price in 2016 is $1.33. So if I want the coefficient of variation, CV, it is equal to, for Facebook, right? Oh, let me write that. Well, I'm on the left. So for Facebook, the coefficient of variation is the standard deviation, 4.67, divided by the mean, 114.73, times 100%. And Facebook's coefficient of variation is 4.07%. Then for Twitter, the coefficient of variation, the standard deviation, 133, divided by X bar, the mean, 16.06 times 100%, is equal to 8.28%. So using this metric, this third measure of variability, we find that there was more relative variability for Twitter. So its price was lower and its variability was lower, but technically it was higher. And the reason for that, the closing prices of Facebook were, relatively speaking, meaning because they were higher in cost, but they were still more consistent. Because the mean closing price for Facebook, 114.73, is 7 times greater than Twitter, but the standard deviation for Facebook is less than 4 times that of Twitter. Okay, so if that was a little bit complicated, basically Facebook has a higher price. They're allowed a little bit more variability. Twitter has a lower price, but their variability wasn't as low as we would have expected it to see. Facebook was more consistent. Okay. Ultimately, it boils down to, can you compute these different things? I hope you can. If you have questions, please let me know. Work on the homework in my math lab. Thank you for watching and have a wonderful day.